This is video tutorial 11 on explicit dynamics. In tutorial 10, I took a very simple L-shaped part and dropped it on a rigid ground. So this is a continuation of that kind of a tutorial, except that instead of a simple L-shaped region, I will take an assembly made of something that you see like here. Okay. Now, the dimensions are given there, okay? And I want to point out to, by the way, the fact that this is made of two pieces. There's something that you can call a camera or a poor man's cell phone, and then there's a lens here. The frame is made, the big frame is made out of aluminum, and this which is subject to elastic plastic response, and this lens, think about it as lens, is made out of elastic brass. Okay, so the dimensions are given here, and the only thing is that when I drop this initially, I make sure that when it hits the analytical rigid surface down here, it hits it on a line, which means there's an initial line contact. Now, I will do that, but then I will also come back and tilt this analytical rigid surface a little bit, so that when the camera is dropped, it will hit it at a point. And because it's hit on a point, then it kind of wobbles around. Now, the gravity is also going to be acting here. We'll see that. Uh, the only thing is that when I do this thing so that it's dropped on a point and it kind of wobbles, I will just show you the result, which takes about 20 minutes to run. So I will just show you the video associated with that. Okay. So this is the one that I'm going to show you right now. Uh, this is dropped and it's going to land on a line basically. There's going to be a line contact. Uh, there is uh, the assembly is made of the camera, the lens, and analytical rigid surface. It's a very coarse mesh, and therefore the results are not reliable as far as the artificial energy is concerned, because of the size of the mesh and things like that. There is going to be a lot of artificial energy generated there. So if you want to do a more reliable answers, first of all, you have to take a finer mesh and also have a better perhaps material data also. Okay. Uh, the mesh is made of this kind of a hex elements. The details are given here. I'm going to follow these, and a material. This I call it a lens, but I'm using the brass properties for that. Aluminum casing, and the details of the mesh is given there. For aluminum, we need because we're doing explicit dynamics, we need the density, and I'm going to use a damping mass damping factor, and this is elastic data, and for brass is just a simple elastic material and density. Now this data comes from a video on YouTube, which is down here. Just some information that I'm just collecting from that website. All right, explicit dynamics, total duration of 0.1, and these are the kind of elements. We're going to use the reduced integration. Gravity is going to be acting 9.81 downward, and there's going to be an initial velocity before it hits the ground. There is a velocity of -1 meter per second. Now, I can make this thing fall from a height, but then it's going to take a lot longer. So I'm going to bring it down so that it has initially contacts that slightly above the plate, and then give it that initial velocity instead of dropping it from a height and nothing happening until it hits it, etc. There's going to be contact interaction general contact interaction between the assembly and the uh, the camera assembly and the analytical rigid surface. There's a coefficient of friction 0.1, and uh, that's pretty much it. And this is the information that ask additional information that I asked from the 3D experience. Basically, it's the basic stuff from stresses, strains, etc., and the energy, because I want to have perhaps a quick plot of the artificial energy, etc. Now, this is the second part of the video where I tilt this slightly so that when it hits it, there's going to be a point contact, okay? But I'm not going to run it, okay? And we'll come to that later on. Notice that this is the result for that second run, which you're going to see only the video of it, uh, recorded video, and it took about almost 20 minutes to complete. The one that we're doing takes maybe 3-4 minutes. Okay, let's go ahead and make it. Here is the 3D experience interface. Let's do the frame first. So put the cursor there, right click, insert, and I'm going to do a 3D part, and that's going to be the frame with the dimensions that I showed you there. Okay, double click. All right. So on that vertical plane, I will sketch. Uh, the camera, or not the camera, well, I'll call it that, the rectangle. So centered rectangle, something like that. We put some dimensions here. So let's see now. This dimension, this is a 100 millimeters. That is 50. Okay, there's going to be 4 fillets here, and the easiest way to do the fillet probably is to select all of these. Well, actually, where is that? Let's go and get the fillet. Here's the corner. I select all of these, and it's going to put it at all 4 corners. I'm going to change the dimension. Okay, so this dimension, let me see, does it say 10? 10. Okay, very good. That's what you got. Now I'm going to draw the that place where the lens is going to go. Okay, and this radius obviously is going to be 10. Okay, I don't have to actually dimension it because it is going to be 10. It's tangent to that. And let me see, maybe I have to dimension it just a second. Is it 10? Oh, I guess I have to dimension it. Okay, 10. Very good. Exit. Exit. And padded by, the thickness of that is 10 millimeters. So we're going to pad it, and I'm going to pad it in both directions. Notice that we don't have to go to generative part design. Sorry, we don't have to go to part design in order to make a solid here, because there is this feature of making volumes there in generative shape design that I'm at right now, or I can do that right here, or you can go to the part design. So it's going to be 5 millimeters, and I'm going to do a mirror extent. So it's there we are. This is the this is the frame. Okay. Now let's go. Oh, let's do the material while you're at it. Let's do the material here. So tools, uh, create material. I'll call it the camera frame, which is actually aluminum, uh, aluminum, almost the aluminum properties. We say okay. Oops, put some date here, October 29, 2023. This is so that I can find them easier. All right, so let me do a refresh, and it should be somewhere here. Camera frame, October 29th. Okay, very good. So apply, get to this, apply to that part, green check mark, and now we're going to go to material. Okay, so structural, uh, general option, density. We need the density because it's going to be explicit dynamic calculation. All right, that takes care of this. Abacus multiphysics, mechanical, elasticity, elastic, and the Young's modulus, as I showed in the slides. The Young's modulus is let me see for a second. It is I believe it was 79,000 MPa, 79,000 psi. Sorry, 79,000 MPa. Yeah, 79000 MPa, Poisson ratio 0.33. Okay, 0.33. All right, and then we're going to go to damping or plasticity. Let's go to plasticity, metal plasticity, and there is the plasticity data. So those numbers, there is 150 MPa, plastic strain of 0, 250 MPa, 0.05. Next one is 350 and plastic strain of 0.1. And 500 MPa, plastic strain of 0.75. Okay, finally damping. Damping is down here. Damping, we are only doing a mass proportional damping, and it's 25 hertz. The unit of this coefficient is 1 over second, or radians per second. I think it's radians per second. 1 over second, which is hertz. Okay, that takes care of all of these. We close that. Now we're going to go and insert, go all the way to the top, insert the lens, insert the insert 3D part. This is going to be the lens. Now we can create the lens right where it is, or I can create it somewhere else and then I move it here and assemble it. Okay, the choice is yours. I'll make it right there. So on that, let's go to the part 3D shape. On that plane, on that what is that, YZ plane? Is this right? YZ plane. We'll sketch. Because it's the same size. What I'm going to do is I'm going to project. I'm going to project that circle. Okay. The only thing is that if you project it, you can't change the radius of it, but that's okay. We don't want to change the radius. So under sketch, here's the project. We take that circle, we project it. Did it get projected? Yeah, okay. You say fine. So it's projected there. Actually, you can see that there is a red curve there. That's a projection. Okay, so we exit, 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 and then we create a volume, pad it in both direction, and 2.5 millimeters in each direction. So there is the lens right there. If you want, we can change the color of it. Let me do that. Properties, graphics. Let's change this thing to some different color, maybe Beige. Okay, good, good. We apply material properties. So we go to tools, create a material. I'll call it lens, brass lens. How about that? Lenses are not made out of brass, but that's okay. October 29, 2023. Okay, let's refresh this thing. Lens, camera, brass lens right there. Apply. Okay, let's double click on it. Structural, we need the density of it. For density, I believe I took density of the brass, I took roughly 1500. These are just dummy numbers. I just put some dummy numbers there. I don't know what the exact density is, but anyway, abacus multiphysics, mechanical, elasticity, elastic, and the Young's modulus is 10,000, 100,000 MPa. For aluminum, it was 79,000 MPa. Yeah, and Poisson ratio 0.34. 0.34. These, as I said, these are just mock numbers. Okay, let's do a quick save here, all the way to the top. Quick save. Now we're going to create our analytical rigid surface. Okay, so we're going to insert, right click, insert, insert uh, a, a 3D part, and this is going to be analytical rigid surface. I have two choices. I can make the analytical rigid surface horizontal and then tilt this thing a little bit. That's a possibility. Let me actually do that. You know, let's try doing that. Let me make on that vertical plane. I will sketch. Okay, I will sketch a uh, a line which after extrusion is going to be my analytical ridge surface. Okay, so exit, and then we pad it on the surface tab. We can extrude it in by, let's say, by 20 millimeters in each direction, something like that. I mean, to make sure that this thing won't fall off that, we can make it even longer. Bottom, making it 30. Okay, that sounds good. Now, uh, I'm going to tilt this thing a little bit. So we go all the way to the, oh, let me create a point here because it's going to be my reference point. So although I can use one of these vertices as the reference point, but I'd rather do that here, wireframe, a point, and I'm going to give it some height of maybe 20, 30, and 30 millimeter, and an X of maybe oh, so a Y of maybe minus 40. Let's see how it looks like. Yeah, okay, that's going to be my reference point. That's fine. Okay, good. Uh, Now we go all the way to the top. So I'm going to do a couple of things. Rotate this thing a little bit and then bring the whole thing down. Now you can do it one by one. If you go to the manipulate tab, see the manipulate tab? Manipulate, manipulate. The only thing is that I don't know whether I can do them at the same time. Let's see now. Let me select both of these. Sure doesn't look like it. Let me see if I can see. Bringing it down is no problem. It's just that by how much? So let's see now. Can I do that at the same time? This control that. I don't think you can because notice that one of them is going to come. So here's what I'm going to do. Cancel that. The other option is to move this thing up, or I can put a constraint here and then bring it down. Let me do that. So here's the engineering connection. Let's make a constraint here. Yeah, just bear with me for a second. Okay, so we want the coincidence. Okay, so here's what I'm going to do. I'm going to make that uh, axis and that axis. Okay, and these other ones, I don't care. I'm just going to close them. This is just a constraint, access to access constraint. We say okay, okay, fine. Now we're going to go do manipulate. Make sure that this is checked. Respect with respect to constraint, and bring this thing down first of all. This whole thing down. They go together. You can do it any way you want. Let's put this thing in the and rotate it a little bit. Rotate about that'll be the x-axis. Yeah, something like this. And then we're going to bring it down so that they actually have contact with each other, almost in the contact position. So to do that, I'm going to put this thing in the front view right there. Okay, and then bring it down. This is bring it down. See, I want to minimize the travel distance as much as possible. Yeah, as long as it doesn't go through. Okay, that's fine. Okay, okay, good. So all the way to the top. Let's save everything. Okay, good. Now we're going to go to the meshing to the top left corner, 3D or VNR, either way, structural model creation. Both of these are subject to, yeah, okay. Oh, what it was saying that because I moved things down, it was not updated. If it's bothering you, you can go and update it. Let me cancel that for a second. Cancel that. Let's update it. Now do that. Now go to structural model creation, empty FEM model. Both of these are subject to hex extrude or sweep meshing. It says that there are 3 parts here. You want all of them to participate. I check this, everything is participating. And here is the mesh, and here's the sweep mesh right there. So let's do the frame first, and I have the numbers that I had there. Let's see now, the numbers that I had were for the frame, it was 3mm, 3 layers, okay? 3 meter, three layers. Let's go back here. This is 3mm and 3 layers. Mesh. Good. Say okay. While we are at it, let's do the properties for it. Properties. Let me unpin this so that I can see. Okay, there we are. So you select that frame. The entire volume material is properly selected right there. Good. Okay. And now we're going to do the meshing for the lens. So once again, mesh, sweep mesh. Right there. And the size is 2mm, 3 layers also. So that's going to be 2mm, 3 layers, mesh. There we are. apply material properties to it. So properties, solid on the lens, pick volume, that's fine, brass. Okay, good. And now we want to declare this thing as analytical rigid surface. So we have to select the abstractions tab right there, see, abstractions tab, and down here under this you have either rigid body, I can make this thing rigid body, which I don't want to do that, or analytical rigid surface. You click on analytical rigid surface, you select that surface, and for the point, reference point, you highlight this and select that point. Okay, that's pretty much it. Let's do a quick save. All right, and now because we want to do explicit dynamics, we have to go to the mechanical scenario creation right there. The software says you want to do what kind of analysis you want to do. It's structural, and the mesh is the one that we just created right here. See 17129, 17129. This is the mesh that we created. All right, almost. Okay, so there's no procedures. We're going to select the procedures tab. It's going to be explicit dynamics, and duration is 0.1, 0.1. Okay, we're going to clamp that entire face. So under boundary conditions, there is either clamp or fixed displacements. All displacements are 0. It's easier to see what's going on that way because the icon for clamp is just a big yellow ball. It's just hard to see. Okay, this is clamped. Now, what do we now? Initial conditions. Initial conditions. Velocity, right? Initial velocity for both of these parts. So for two parts essentially. Let me do it from the tree. We can do it from the tree. It's easier. So it's this part. This is the camera itself. And for the other one, it's the lens, part body for the lens, both of them, given initial velocity in the z direction of -1 meters per second. Okay, so that takes care of this. Okay, we are acting gravity. Gravity is acting, so you go to loads, and there's the gravity. Once again, you can select the part bodies. Part bodies, this one and that one. Two part bodies are selected, and the value is -9.81. Yeah, downward right there, and I just want to check something here in the drawing. Yeah, that's the icon for gravity, and the reason that you have these two green arrows because both of these obviously parts are subject to gravity load. Okay, now we go to the interaction. So let's go to the interaction. First, define the contact property between the surfaces, and I'm going to put a friction coefficient of 0.1, 0.1. Okay, and we say all right. Uh, yes, and then it's going to be general contact. Everything is contacting. Uh, and the contact property is the one that I just did. Remember, coefficient of friction of 0.1. Select this and say OK. And unless I forgot something, I think pretty much that's it. And one last thing that I want to do is we go to simulate. This is where you request your data. So click on the output. I want the stress, strain, displacement, force, and contact information. Every 200, I don't know what I said, every 100, 200, let's see now, every 100, yeah, every 100 intervals, okay, that's this. This is the field information, and another one for the history information, energy, and every once again 100. Say okay. Let's save everything, and we're gonna run it. I always tell the students to pray because when it comes to running things, we find it with software. Occasionally people forget, etc., etc. Uh, there is one thing that I forgot to do. Let me see. Maybe not. That's fine. So let's go ahead and simulate. This is model check. No issue. Simulation check. We'll see. Okay. This is going to be fast. Running, I would say about maybe 4 or 5 minutes. Ooh, there is an error here. Let's find out what the issue is. Okay, there's some information that they asked to be obtained, but it's not available. So let's find out this thing. CS. I'm not even sure what that thing stands for, but anyway. So let's go ahead and do this. Let me close that. Output. Okay, actually, let me cancel that. This is the stuff that we requested. So under our scenario, here is the output request. Okay, let me first of all get rid of these last two that I didn't want. Don't know why. It's that thing that I clicked that caused these things. Let's go double click on this, see what we've got. So this variable that we're asking must be in something here. So what I'm going to do is, let me see for a second. Let me uncheck that. See if we can find this. Not there. Okay. All right. So let's go ahead and do a simulation check one more time. I expect this error still to be there because I didn't actually find that variable. Let's see, we'll find out. Okay, maybe it was actually in that contact. I think I eliminated contact request there. So let's run it now, see what happens. This the running hasn't started yet. As soon as the dialog box appears here with the OK button in it, and once we press the OK button, then the the simulation begins and the analysis basically starts running. Now we're going to now right now once we click this, then the simulation begins, the actual running begins. Now there is this box here which says this tab here, iteration. This is the equivalent of the monitor in the Abacus program, or generally speaking, Abacus, Abacus CE program. Okay. The first two that we did, model check and scenario check, were actually your data check. Okay. All right. So let's see now. I'm expecting this to go kind of fast, maybe about mostly 3 minutes. If I feel that it's taking longer, then I'm going to stop the video and come back and start it again when we when it's done. But I think this should be okay. Yeah. So notice that already 41,000 steps have been taken, and we are at point zero. The wall clock is here. It took 41 seconds. Okay, and we are. Remember, we have to go to point 1. In other words, 20 times more. Let's check for a minute, and then I'm going to stop this. Okay, stop the recording. Okay, so I suspect the next one is going to be 0.001, which means that that's right. So it's going to take 10 times as long here, which means about 800 seconds or 5 minutes. So I'm going to stop this and come back when it's done. Okay. See you in a minute. Okay, I started the recording again, so it's 94% complete, and it has been about 10 minutes now. So it's going to finish very soon, maybe in less than a minute, and we're going to see what happened. Okay, so you see 94%, 532 seconds wall time. Okay, and yeah. At this point, the software has taken almost 750,000 steps of integration. This is the number of steps. Okay, extracting the results took 10 minutes. All right, so let me close that. There we are. This is dropping on its line edge. Okay, this is the initial, of course, initial increment, and then it hits the the surface and bounces. Okay, let's animate this thing. And you can slow it down. Where's this speed? Slow it down a little bit faster. Okay, so here is uh, the one with the stress. If you do the plastic strain, the plasticity only takes place at the aluminum frame, because this piece, this lens, is actually elastic. And of course, displacement is obvious. Now, what I'm going to do in the second run, I'm going to tilt this whole thing a little bit. Let's get rid of this. Let's go back to our model here. I'm going to tilt this thing a little bit, and how I'm going to do that, because I already put some constraints here, but a constraint between the axis of these two things. Let's go ahead and they're going to stay together. So we go to assembly. Here's the assembly, And let's do a rotation, manipulate, keep the restraints, and rotate about the, what is that, about the Y. Let's take it and rotate about the Y. See that? So I can do a little bit more. And if I feel that they have interfered with each other, this has penetrated that, I move it a little bit up or reduce the amount of rotation. So let's look at the view from the side. You see that it's already, there is some penetrations here. So I'm going to move this thing a little bit up. Okay, now this is going to involve a point contact, because if I look at from the right or the left, you can see that there's a point contact there. Now I'm not going to run this thing, but there is something before we run it. Is I'm going to take the friction out. Okay, so let me go ahead and take the friction out. Where is that under interaction? Let me close these things so that I don't see them. Okay, so under interaction, double click on interaction property, friction. Either you make this thing very small or literally zero. That's one option, making this thing zero, or when you did that, you could have selected, instead of connection property one, you can select the default one, or the default. Okay, you can select the default one, but the default, I don't see it here. So anyway, I made zero right there. All right. So I'm not going to run this thing, but I'll show you what the result of the run is once I took the friction out and tilted this thing a little bit. Okay, this is the video for the plastic strain in the two parts. The lens which slides out, there's no friction here, is made of an elastic material, and therefore it doesn't go into plastic mode, and you can see that it's all grayed out, okay? The biggest stress, obviously, the biggest plastic strain is at the point of contact down below that you see. Let me also show you the displacements here. So let's stop this. Uh, do a displacement. Okay, so let me zoom in. Let's get back and play it. This is the magnitude of the displacement. And as you can see, the lens slides out, and the biggest displacement is going to be for the lens because it moves so much. But obviously, in order to assess the validity of these things, the material modeling must be correct. There should be very little artificial energy here, and therefore one should check the energy balance, which I have not done, and also make sure that the mesh is fine enough. And in this case, I'm pretty sure it's not fine, because I just wanted to make it run as fast as possible. And This was a 0.2 second of duration in the explicit dynamics. Now, if I had done 0.1, I would not be able, may not be able to see the lens sliding out, uh, or if the friction, there is any friction here, or maybe even if they're tied, then obviously it's not going to slide out. If the friction is small enough, very small, then it's as if it was not, as if it was frictionless. Okay, that's pretty much it.